All right, so in this video here, we're going to check out the laws of proportionality and the current divider. You're going to find both of these in your DC theory textbook starting around page 158, and it goes through page 161. These two laws apply to both voltage and current. So this voltage law, it's useful because it helps you fully understand what's happening in a circuit. We'll walk through it, but I'm just going to let you know right now, the real game changer is definitely the current divider. That law will make solving combination circuits a lot faster. Since I plan on doing a couple combination circuits, I plan on using the current divider in there, and I want to introduce it to you. So let's start with the voltage version. So when we know the source voltage and we know the individual resistor values in a series circuit, you can find the voltage drop across each resistor without finding the total current. Since voltage is directly proportional to resistance in series circuits, this works almost like calculating a percentage. So the formula in the textbook looks like this. EX, so X is just whatever voltage value you're looking for. If I was looking for the voltage of E1, you just type in E1 there, and it's going to equal the total voltage, and that's going to multiply by the resistance of R1 over the total resistance. So let's apply this formula real quick and see how it works out in practice. So we have 480 volts total at our source, and I'm going to multiply this by, let's find E1, so the resistance of R1, which is going to be 40, and we are going to divide this over the total resistance, which we have 80, and then equals. You could type it in the calculator like this. $240 volts. So let's think about this a little bit. If R1 has half of the total resistance, it only makes sense that it is getting half of the total voltage dropped across it. And that is pretty much the law of proportionality when it comes to voltage. Resistance and voltage in series circuits are directly proportional. And if you think of it as a fraction, like 40 over 80 equals 50%, it is going to see 50% of the voltage. Let's use this to find E2. So source voltage times the value of R2 over 80. See what this is. $180 volts. So E2 is going to equal 180 volts. All right, so let's try this. Total voltage minus E1, which is 240, plus E2, which is 180. So doing that math, we should have 60 volts dropped here using Kirchhoff's voltage loop rule. If I'm dropping 240 and I drop 180, I got to drop 60 here to hit 0. Let's see if this formula works out for this. So 480 times 10 ohms over the total resistance. $60 volts. I like knowing how to do this, but I'm not really using this very much in solving any circuits. It's definitely good to know more of your electrical knowledge, how electricity works. So one more thing I want to talk about before we get onto the current law. I'm using a website called Circuit Lab to build these example circuits for these videos. So it lets me set up everything using clean whole numbers. If I'm able to make my circuits, if I can, I'm definitely going to have whole numbers for everything. You'll notice we do the same thing in class. It's not because real world avoids the decimal points. It simply just makes sure that you're confident in the process itself. without getting hung up if I should round this decimal point or where do I got to end this decimal point. In the couple videos that I plan on making and all the circuits we do in class, I've figured out everything to where most of the time everything is going to be a whole number or it's going to have like one decimal place. No need for rounding. I just want to make sure you're confident in the process itself without getting hung up on messy numbers. And then once you understand that this method works and why it works, then when you start getting into decimals, like in the circuit challenges and on the tests, you'll realize that they're just numbers. You know what you're doing. Hopefully you build enough confidence that you're not getting stressed out over the test. You're going to know that you know this 100%. So let's get into the current divider. This is the current divider right here. In the textbook, they give you a couple different current divider formulas, but I found that this one works pretty good with the combination circuits. So if you notice, if I am looking for the current through I1, I have the resistance of R2 as the numerator in that fraction. So if you decide to use this formula here, you got to ask yourself, if you have 12 volts coming into this junction, and we have two resistors, we have a 48 ohm and a 240 ohm, which one of these branches is going to see the higher current? It is going to be this one here, the one with the lower resistance. The more resistance, the less current. So back in my 2024 class, I had a guy named Kyle K, super smart dude, who pointed out something that simplifies this whole process. He said, since this is just a proportion and the total current has to be split between the two branches, 100% of the current, you can flip this approach. If you take the ratio that uses the resistor that you're solving for in the numerator and just subtract it from 1 being 100%, you'll get the current through that branch. His version looks like this. This dude was using this formula here with extremely difficult combination circuits, and he was solving them in like a minute. It was definitely the fastest I've ever seen anybody solve these circuits. So here's the idea. It's the exact same equation, but putting the resistor you're interested in the top and using 1 to represent 100% of the current makes it a little more intuitive. Once I start making videos that involve combination circuits, I am definitely going to show this method. If it clicks for you, you'll be running through these circuits in seconds. So what this is saying is if I am looking for the current through I1, what I'm going to do is I'm going to take the current that is heading into that junction and I'm going to multiply it by 1, which represents 100%, and I am going to subtract the resistance of the branch that I'm looking for, which in this case is going to be 48. I'm looking for I1, and I'm going to divide this by 48 plus 240. Notice that I'm not combining these in parallel. They're just going to add together like this. This should equal what? 288 and parentheses. Let's type this in the calculator. 12 times parentheses 100% minus 48 over 288. 10 amps. So if we have 12 amps coming into this junction and we have 10 amps coming down, that means this branch here has got to see 2 amps. Let's see if the math works out. 12 amps total times 100% minus the resistance of the branch you're looking for, 240, over 288. Both of those resistances just added together. This should equal 2. 2 amps. All right, so Kirchhoff tells us that we have 12 amps coming down, 10 amps go this way, 2 amps have to go this way. What enters a junction and leaves that junction has to equal 0. These 2 amps are coming down, they're going to come back around this way, they're going to meet up with that 10 amps, and then all 12 amps are going to come back to the source. I just wanted to throw a quick video together to introduce this concept for you. This formula here is a game changer. Kyle wasn't even using voltage to solve his combination circuits. He just found what his currents were in each of his branches, used the current with the resistance, had those circuits solved. It was pretty cool to see. Anyway, thanks for watching.